So I'm going to do this here. Now, can someone tell me what is the first moment of area that we're going to take? Anyone? Are you all there?
From the bottom of the beam to the, I'm sorry, I'm not describing this very well. The bottom of the bottom flange to the top of the top flange, not including the webs.
Yeah. Okay. So okay. The confusing thing is this. Okay. The confusing thing is this. Vy was you come from what? Come from the top, right? And if you see the shear flow Q is still flowing in that direction. That is the right direction. Okay. Nothing changed. Okay. That is the right direction. Nothing changed. Okay. But because mathematically our issue is the first moment of area. So let me further elaborate. Okay. So this is our centroid, and based on the rules, we said that the centroid always starts from the datum is at the what? Is at the centroid, right? And we always states that what? The analysis, right? The analysis will start from where? Y max. And the analysis direction is going to be towards the what? Towards the datum. The analysis direction is always going to go towards the what? Towards the datum. So if we apply the rules like how we derive the expression that we did, so we derive on week 3 we derive this self-expression, right? We derive, right? We derive the first moment of area from this expression. We set up the rules. Okay, so from here, if we were to do, so coming back to here now, right? Okay, so we know that y max will start from the maximum at the bottom, and once this variable start to what? Reduce, right? Let's say it hits here, it covers the entire it covers the entire area of the what? Of the flange. So let's say your y keep on contracting, right? Keep on reducing, right? Because your y will start from maximum, then it reduces. So at this point, when it is reducing, it completed the what? The area of the what? The area of the bottom flange. But the web, right? The web has not completed covering the area yet. Okay, so that is why we only, when we look at the first moment of area, we only consider the what? Consider the bottom flange only, right? Right. So your y start from maximum, it slowly retract. At a certain distance, right? Where it's retract, it covers the entire area of the what? Covers the entire area of the bottom flange. Okay. So the web, the area is not covered yet until y is equal to 0. Then the entire web is covered. So for this reason, that is why you only consider the first moment of area of the bottom flange. The confusing thing is this. It's all this arrow. You will tell me, Eugene, see the arrow is here, it's transmitted, yes or no? It's flowing it's flowing towards the what? The bottom flange. You're right. I'm not saying that you're wrong. But mathematically, to get the first moment of area, okay, you just need to consider the bottom flange. Okay, or if not, it get really confusing. You would say, Eugene, why not I take this I should use different color. Why not I take this area down here? Why not I take this? I also include this area. Yes or no? Right? Why you don't include the area that I shade in red is because of what? The bottom flange, the fastener is only to transmit the what? The load. The bottom flange will distribute the what? The load. Okay, you have to be very critical about this. The bottom flange will distribute the load. The fastener will need transmit. Okay. Now, Any questions so far? I know this is pretty abstract, okay? So these are the rules that you really have to oblige. Anyone, any questions, please? Or you want me to repeat something? Anyone? No one? We are good? Okay, so failure at the bottom flange. So from here, right, the Q is still the same, right? So the Q due to the fastener is still 50 pound-inch, right? So now you want to find the QZ of the bottom flange, right? So this is equal to width multiplied by diameter multiplied by y bar. So the width for the bottom is 6 inch, the depth is 1, and then the distance, so we know that from here to here is 3.1. Yeah, I hope to get this right. 3.1. Did I say 3.1? Yep. And then the distance, the overall distance from here to here is so 5, 6, 7 inch, and the individual centroid from here to here is 0.5. So what we have is 7 minus by 3.1 minus by 0.5. That will cover my distance from here to here. That is your y bar. Okay. So from here, we get 7 minus 3.1 minus 0.5 times 6 times 1 is equal to 20.4 inch cube. Yeah, I think we are in inches. Yes, we are. And then finally, pretty straightforward, right? So Q. So once you get your first mole of area, that's where the most confusing part is. So now you have Q will be equal to V. V is what we identify. Q is now 20.4. I did not change, which is 197.7. And then finally, you have your Q due to the fastener, which is 50. We have calculated. So therefore, V will be equal to 50 times by 197.7 divided by 20.4. So this will be 484.6 pounds, or 485 pounds of force. Okay. So the top flange will fail. The top flange fastener will fail at 317 pounds. The bottom one will fail at 485. So the control, or the V allowable, will be equal to 317 pounds. Okay, so this is the one that controls the structure. Okay, so there's a, if you were to pick the 485, the top flange will fail already. Okay, the top flange will fail. Any questions so far? Anyone, please? Confused, or you guys are clear? Anyone of you are confused, or you guys are clear? So what is the saving grace? So that usually when you look at the top, we don't have problem. The confusing part is the bottom. But if you apply the rules that are specified, it's no more so confusing anymore, right? The 4 rules. And the 4 rules is derived in the first week, the first time I taught this lecture, yes or no? So I hope you all will like have an encouragement to look at the how the equations are derived. We only create those rules after we derive the set of equation, yes or no? In week number 3, we go into derivation first, like how to prove this function over here, right? And only by deriving we come up with these rules. So I hope from here, with anything that you study or any courses, look at the formula seriously and try to derive it out if possible, because you will learn a lot. Okay, by deriving it, you set your rules. By the set rules, it can be regardless of how complicated it is. I know you'll be fine. Okay, I know you'll be fine. Like now, okay, let's look at another example. Okay, so this example is pretty confusing. Even I myself have issue with this example without the rules. After I make up the rules, it is so straightforward. Okay, so now let's look at example number 2 now. Okay, so let's go into example number 2. Okay, so we have, I hope, copy the wrong thing, Eugene, for crying out loud. I wonder why is that there, but anyway, copy. Okay. How many of you on your own time that you have helped your family or you have built a deck before? Anyone? Did anyone build a deck before? Anyone? No, no one built decks. Helping family build a deck in
Yep.
your yep, you have built a deck. Only one have built a deck. Okay, right. I did a lot on consulting about how to calculate stresses on a deck. Okay, and this is one topic, or this is the chapter that I apply a lot on how to calculate stresses on a deck. Okay, so I will come to you on that. Right. So what you see now is the timber beam is subjected to a 1,500 vertical shear. Right. So shear force 1,500 pounds. Knowing that the spacing of the nail S is 2.5 inch. So S is 2.5 inch, the spacing. And that each nail is 3.5 inch long. Determine the shearing stress in each nail. So the 3.5 inch is the nail, the geometry from here to here is 3.5 inch. Okay, so it's telling you that the nail is holding. Okay, the geometry of the nail is longer than this block down here, right? Than this block down here. Okay, so if we look at the problem, so some of you have built a deck before. Those of you have not, it's okay. Right? So my question is, how will the length of the nail affect the loading? Anyone, please. There's an optimum distance of the nail. Okay, for this case, the nail has to be 2 inch long, at least. If it's less than that, it's completely useless. Longer than that, fine. So how does the 3.5 inch help in our structure analysis? Anyone? How does the 3.5 help?
Because it's less than 4 inches, then it's in single shear instead of double shear.
Okay, so yep, it will help you in single shear or double shear. Okay, what else? Is it necessary the longer the better? Besides single and double shear. So let's say now you have single shear configuration, and you have a choice of nails. One that's longer, the other one that's shorter, but both are at least longer than 2 inches. What will you buy? Will you buy the longer one, or will you buy the shorter one that's greater than 2 inches? Anyone?
The longer the nail, the better the holding.
Show me the formula.
experience. That's just
No, does not matter. There's no. It only will help if once the joint is separated, we call it failure already. Okay, does not need to collapse. I repeat again, once the joint is separated, okay, it's failed already. Okay, so the length of the nail